MODPIE is a toolset designed to help system experts pose performance questions and decide on the optimal architecture for a system execution model or SEM. We will be executing an existing model of an unmanned aerial vehicle or UAV to demonstrate the functionality of MODPIE. MODPIE is broken up into 5 phases: modeling, deployment, execution, observation, and analysis. The first phase is modeling. The Generic Modeling Environment, or GME, is an off-the-shelf and open-source modeling tool. In GME, the system expert constructs a model representation of a distributed real-time system. For each software component in the system, a component interface is constructed. This UAV model has a GPS, controller, and comms component. Each component contains a set of input and output event ports and a corresponding behavioral model. This information is modeled in accordance with provided documentation and specifications of the system. Each component has its own unique behavioral model which serves as the business logic for the component. Each input event port can have a chain of events attached to it, which is executed every time a message is received on that particular port. Actions can be used to utilize CPU resources, allocate memory, and log information about the component state. New messages can be created and sent through the output event ports to stimulate other components in the system. Branch statements, state variables, and periodic event generators can be used to implement more complicated business logic. Once each component is modeled, the system expert then creates an assembly for the system, creating implementations of the component interfaces and connecting the input and output event ports to form a system of components. The second phase is deployment. The deployment generator tool is designed to produce a deployment configuration which describes how a SEM is to be deployed onto a particular hardware testbed. The system expert chooses which middleware the SEM will use to implement the connections between components in the assembly. All of the components from the SEM are then imported into the tool, along with all available hardware nodes. The testbed of hardware nodes are running an array of different operating systems, architectures, and hardwares, ranging from powerful multi-CPU servers to lightweight ARM machines. After the components and nodes are loaded in, the system expert is then able to connect and select the SEM components to hardware nodes. The system expert may have to deploy software components from the model onto a specific node to adhere to a non-functional requirement provided. The SEM and deployment configuration is then put into version control by this tool and is used by the execution phase. So the third phase is execution. We use Jenkins as our continuous integration server to streamline the execution of the SEM. Jenkins has been configured and scripted to manage the nodes in the hardware testbed. It controls the distribution, compilation, and analysis of the execution of the SEM. It is a framework which provides robust executions and repeatability. The system expert executes the build job with the SEM and deployment configuration under version control used as a parameter. The user is also able to choose how long the SEM will execute for. The Jenkins infrastructure generates the C++ code for the SEM and distributes the code to the targeted nodes. The code is then built natively and executed concurrently. The fourth and fifth phases are observation and analysis. The visualization tool has been designed to run on a multi-touch input system and provides an immersive way to understand the performance impacts of executing the SEM. It runs concurrently with the SEM and provides real-time visualization of the component and nodes utilized in execution. In this video, we are seeing the real-time output from the execution of the UAV model. The tool is able to monitor the network traffic, CPU and RAM utilization of each hardware node, and visualize the messages being sent between components. Bottlenecks and hotspots and component connections are also visualized. The system can also calculate aggregations, for instance, allowing the user to determine the average ping over the critical path of the system. The tool provides a visual insight of the performance of the SEM execution. Through the use of the MODPIE toolset, the system expert is able to model, execute, deploy, and analyze a model representation of the system. It provides early insight into the architectural characteristics and helps to provide potential improvements for future iterations of the system.